All right, so we want to find these two definite integrals using the fundamental theorem of calculus. We want to integrate 1 over x from 2 to 12 with respect to x. We also want to integrate 200e to the point 0.05x with respect to x from 0 to 10. Let's do both of these. I start by integrating 1 over x from 2 to 12. 1 over x, if you recall, is that special function where if you take the antiderivative, it needs to be natural log of x, or the natural log of x plus a constant. We'll use a constant of 0 just because that's the easiest. We're going to be integrating from 2 up to 12. That means what I'd have to do is take natural log of 12 and then subtract the natural log of 2. I type that into my calculator all at once, otherwise we're going to get some ugly looking decimals. So natural log of 12 minus natural log of 2. You should end up with 1.79. 1.79, at least approximately. And again, this is something you're just typing into our calculator. Nothing fancy about that. Also, one of the things I didn't mention before is that we know 1 over x is not continuous on the real number line. But the only place it's not continuous is when x is equal to 0, because when x equals 0, we get an asymptote. The function is not defined. So as long as we're avoiding that asymptote, we are fine to integrate from, in this case, 2 to 12. Let's take a look at the next example. The antiderivative of e to a linear exponent is e to that same linear exponent and then I have to take the coefficient and divide it by the coefficient of x in the exponent. In this case, that's 0.05 or 0.05. We will eventually be plugging in 0 and plugging in 10, or if you'd rather, you can say plug in 10, then plug in 0. By the way, 200 divided by 0.05 is 4,000. So we are integrating, or actually not integrating, we have integrated. Now we're going to be plugging in the 10 and the 0 into 4,000 e to the 0.05x. Or you can also write 0.05 if that's more comfortable to you. Let's go ahead and plug in our numbers. I'm going to plug them into the 4,000 e to the 0.05x expression. I won't plug them into the 200 over 0.5. That's just more work than I need. So we plug in 10 and then subtract what I get when I plug in 0. Again, when I say plug in, I mean for x, obviously. I am going to calculate this in one step on my calculator. 4,000 multiplied, 4,000, multiplied times e to the 0.05 times 10 minus 4,000 times e to the 0.05 times 0. E to the 0.05 times 0 is going to be 1. And so 1 times 4,000 is just 4,000. When it's all said and done, we get approximately 2594.89, rounding to 2 decimal places. That's a pretty neat feat to be able to do that. The Riemann sum approach to this would have taken me an extremely long time to get something close to 2594.98. Or excuse me, 0.89. This is how the fundamental theorem of calculus works. Antiderivative, find any antiderivative. We plug in the top bound and then subtract what we get when we plug in the lower bound into the antiderivative. Whatever that number is the signed area of this function between the a and the b values. In this case, it's the area of the function between 2 and 12. Let me show you a visual of that real quick. I have graphed the 1 over x function. I put f of x equals 1 over x. Here it is. Notice we have an asymptote at 0. But our x values are between 2 and 12. What I'm looking at in terms of signed area is this signed area here. This signed area between 2 and 12. That signed area was about 1.79. Again, that's much, much nicer and much, much more efficient than trying to do Riemann sums and getting close to an actual number. So there you go. That's 7-4, the fundamental theorem of calculus. One more little thing that I want to say before I move on is obviously we've been calculating definite integrals, but these things can come up anywhere and with any type of function. Some functions that are inside here are hard to take the antiderivative of. That's what chapter 6 is all about. So there are more complex techniques to find antiderivatives. We'll discuss those later in the semester. We have to get really, really good at the fundamental theorem of calculus.